Let's continue with solving the example that we were working on. So far we found this 6 by 6 global SFS matrix that we want to fill in. We have found the local SFS matrices for the two elements that we used for this example, elements 1 and element 2. And we have also considered a constant E and constant I. We found the relationship between the local and global forces for the nodes, as well as the local and global displacements for the nodes. Now it's time to find this 6 by 6 global SFS matrix for this beam example. So let's first use the local SFS matrix for element 1. Element 1 was only consists of nodes 1 and nodes 2. So node 1 has d1y, phi1z, node 2 has d2y, d2z, as I've shown in here. So what that means is that I only need to use the displacements corresponding to node 1 and node 2 to fill in the global SFS matrix. And that portion of the global SFS matrix is shown by this dashed rectangle. So I just plug in these numbers from the local SFS matrix for element 1 to this portion of the global SFS matrix. Basically, those numbers come in here. No change, no difficult mathematics. And that's because I've shown these corresponding displacements for each node here and there. That shows that this portion of the global matrix is where only nodes 1 and 2 are considered. Moving on to element 2, I only have nodes 2 and 3 for displacements. And that portion of the big matrix is here, again shown by a dashed rectangle. So if I divide this into four 2x2s and show 1, 2, 3, 4, it would be equivalent to 1, 2, 3, 4. And it's easily it can be easily distinguished by looking at the displacements at each row and column. So if I take a look at that, and if I correspond them to these nodes in the local SFS matrix, I can figure out which portion of the big global SFS matrix these values go there. But the point 1, or the portion 1 of this matrix, was already filled with elements from or components from element 1. This 12 was from the previous one, this minus 6, and this 4l squared are from element 1. Let me change the color of the pen so I can easily make my point across. Now this 12 from portion 1 of the local comes and adds to the previous 12. This 6l comes here, and then this 6l comes here, and this 4l2 comes here. So these two will add up. Minus 6l plus 6l will be 0. Again, minus 6l plus 6l becomes 0, and this will be 8l squared. The other components of this matrix were not initially populated, so they are populated exactly with the numbers that are in this matrix. Then I'll have K51, K52, K61, K62, and K15, K16, K25, K26. Because I don't have any more elements and there are no values associated with them, I can just write zeros here in place of these elements. So if I do that, and if I do the summations in this portion of the matrix, I will end up with this 6 by 6 global SFS matrix for the beam. So 12 6l minus 12 6l, and if I take a look at this portion, is when the two elements or the two nodes summed up to give me 12 0 0 8l squared there. And the rest of the elements were just populated with one of the local SFS matrices according to the nodes that are attached to them. So then I can relate the global nodal forces to local nodal forces using this big 6 by 6 stiffest matrix. And again, because I had 3 nodes in my model and 2 degrees of freedom per node, I ended up with a 6x6 stiffness matrix. Now, if I take a look at my problem again, I have node 1, node 2, node 3. Here I have d1y is equal to 0 and phi1 is equal to 0, phi1z. Here I know that m1z is, or m2z is equal to 0, but f2y is equal to minus f. And then here m3z is equal to m, but f2y is equal to 0. And I can put those boundary conditions here. I know these loads, nodal loads from the problem statement, and I know these nodal displacements from the problem statement. The ones that I have written by red are the unknowns of my problem. So I have 6 unknowns and 6 equations that if I solve, I can find these 6 unknowns. So if I assume some numbers, and let me change the color of the pen to not get confused with the blue line. If I assume these numbers for I, E, L, F, and M, I'll end up with this 6x6 stiffness matrix. I just have to put the numbers there in this big matrix, EI over L cubed times this 6x6 matrix. And then I can solve that problem, which I have done using a MATLAB code, which I'll try to show in here. If I can minimize this and come here. All right, so I've written this code in MATLAB. This is the Young's modulus for 2 elements. Then I have L, 3 meters for 2 elements. Then I have I, 4 times to the minus 4 meters squared, or meter to the 4 for 2 elements. Then I find EI over L cubed for all the elements from this line, line 5. Then I find the stiffness matrices for each of the elements, which are the global or local stiffness matrices, using a function file that I've written for beam stiffness matrix, which is in here. Basically uses those numbers that I've put in the equation there to give me the stiffness matrix for the beam. Then I might be in the wrong problem. Yes, here's where I am, or I should be, or the problem that I'm solving. Then I'm using the same function file to get the global stiffness matrix for the beam that I'm solving. And here I'm finding the displacements using the stiffness matrix that I found from the function file and the forces that I applied to it. So I have 3 nodes. 2 of the nodes I know the forces. Minus 1000 force applied in the y direction and no moment in node 2. And in node 3 I have no force but 500 Newton meter moment. And the force, the displacement and rotation at node 1 are 0. So if I just take out portion of my stiffness matrix that I found from line 12 and find its inverse and multiply it by the known forces, I can find the displacements and I can find the forces, global forces from here. And the next thing is just being creative and writing a code to do an animation for this beam, as well as showing the displacement of the beam. So if I run this, my code shows an animation of how the beam deforms, and this is only 3 nodes, so they're not exact. If I close them, these are going to be the total stiffness matrix, or also global stiffness matrix here for a beam problem, and nodal forces, and then nodal displacements, which I've shown in the slide here. So according to the MATLAB code, I get these forces. Let me go back to pen. 1,000 reaction force at node 1, which is equal to the opposite of the local or external force applied to node 2. And then I have 2.5 kilonewton meter moment applied to node 1, which is equal to that 500 times the total length, and then also the effect of this force at its length 3 meter from the base. And these are the local nodal, or not local, global nodal displacements. Node 1 is 0 and d1y and phi1z, and the other nodes have their own values. So we use the stiffness matrix that we found earlier to solve a typical beam problem.